Okay, now we are going to dive off into Experiment 2, the very first part of Experiment 2, which is testing your pet molecule to assign a solubility class so you have some kind of general idea of what it might be. So, this is kind of confusing because it includes acid-base chemistry, which we don't get to until Chapter 6. So I will explain to the best of my ability, but I will begin by trying to give you some announcements. So announcements-wise, you've already started lab. Now we really kind of start in earnest. So make sure you've got your lab coat goggles, no sandals, that kind of jazz. A lot of reading, as I mentioned last week. You'll have to have your pre-lab written up for Experiment 2, but more on that later. And don't forget, you have to take the pre-lab quiz online before you come to lab. Now, what about this pre-lab? What needs to be written up in your lab notebook before you get there? Appendix 4 spells it all out, and then there's a note about notebooks posted on the Moodle site that might help clarify things even more. Basically, the pre-lab information is the title, purpose, any other info that might be helpful, any literature data for compounds that you know you're going to measure boiling point or something, and the names and structures of the chemicals that you're using. That said, you know, you got an unknown. There's really not a heck of a lot you're going to be writing up for your pre-lab. I'd say basically we're talking about title and purpose, and I guess you might as well, mention the composition of the various solubility test reagents, the concentrated H2SO4, etc., so you know what's a strong acid and what's a strong base. But this is going to be a mighty minimal pre-lab. However, if you don't have your pre-lab written up in your lab notebook before you come to lab, you'll turn around and go out until you get it done. All right, survival of this part of the experiment means getting to be friendly with that flowchart in the inside front cover of your orange lab manual. So basically, it is explaining to you what you're doing and how to interpret your results. So we will go through some examples, studying that carefully. The other thing you need to know, and I think you need to know this for your lecture class anyway, you need to know your functional groups. And let me just point out one that's always a little bit tricky for people. An alcohol is an OH group on an sp3 hybridized carbon. A phenol is an OH group attached to an aromatic ring. And a carboxylic acid is none of the above. Carboxylic acid is an OH group attached to a CO double bond. They're all wildly different. Now you don't know what pKa means just yet, but I can tell you that just by looking at these values, you can see these functional groups behave wildly differently. All right, so how does all this work? Well, you're going to get your unknown, and you're going to test its solubility in water. And as long as it's fairly polar, like dissolves like, it'll dissolve in water. But you got to keep in mind, organic compounds are lots of carbons and hydrogens, which means they're non-polar. So a lot of organic compounds are not soluble in water. They have to be highly polar, like glucose or sucrose, a sugar, which has just a ton of very polar hydrogen bonding groups on it. Well, that's not quite right. Don't want to steer you wrong. There we go. So this, table sugar, of course, is soluble in water. Sugars are soluble in water because they've got so many polar OH groups. So they either have to be highly polar like that, or they've got to be really low molecular weight, like C4 or below. And even if it's, something like C4H10, that's nonpolar. That's not going to be soluble in water, at least not to any appreciable extent. So how does it work? You first try to see if it's soluble in water. If it's not, Then we use acid-base chemistry to try and make it soluble in water, because that will tell us what functional group is present. So as I said, you need to recognize your functional groups and understand that it's all acid-base chemistry. In other words, we start with something. This is our unknown right here. We don't really know what the structure is, of course. And then we treat it with something, in this case a strong base, and we go from something that is not soluble in water, because look at, my goodness, it has 1, 2, 3, 4, 5, 6, 7 carbons. There's no way that's going to dissolve in water. And so I test it, not soluble in water. But then when I react it with sodium hydroxide, that's a base. What happens, and again, this is, too much information, more information than you need to know, but you will understand this at some point. That base plucks off that hydrogen, leaving behind an ionic bond, and that ionic bond makes it a lot more polar. Therefore, it dissolves in water. So that's the basic premise. So we'll go through 3 examples to kind of cement this, keeping in mind that I am showing you structures. You will not know the structure of your unknown because it's unknown. Okie dokie. So our first example is the one in the purple box. I believe that is completely an aromatic. That would be the functional group that you would call that would fit into. So the first thing we can do right off the bat is look at our flowchart and see, look at all the functional groups here. Phenol, bunch of these. So I'm going to predict that that particular sample would end up in solubility class I for inert. Now let's understand why. We're going to look at it, test its solubility in water first, and of course it's not soluble because it's C10. No way is that's completely nonpolar. No way it's going to dissolve in water. So we go off in this direction and check its solubility in 5% sodium hydroxide. Now, if 5% sodium hydroxide reacts with this molecule, we would get a salt and it would dissolve. But it does not. Okay, so there's no reaction. So that means not soluble. We keep going. I'll check its solubility in 5% HCl. And again, if there's going to be a reaction, then it will make a salt and it would dissolve. But there's no reaction. So it's not soluble and we move ahead. Well, I'm going to skip ahead. It's not soluble in H2SO4 either, which is even a stronger acid than HCl. The reason it's not soluble and it's not reacting with acid or base is because this molecule doesn't have any acidic or basic acidic hydrogens or basic sites that can be protonated. Again, this is chapter 6. Don't sweat it yet. Bottom line is, just as we predicted from using the solubility chart, this compound is going to end up in the inert class, solubility class I, because it doesn't react with anything. It wasn't soluble in water to begin with. We couldn't get it to react and make it soluble with anything, so it ends up as I. In lab, of course, you don't know the compound. You just do the testing, and if you do the testing, then you see, hey, it didn't dissolve in anything. It must be inert. And it must therefore be either an aromatic or an alkyl halide or an alkane. All right, next example, this is aniline. Now, this is a little confusing because you can see it's both an aromatic and an amine. So what does that mean? Well, let's just go through the flow chart. Basically, we're going to test the solubility in water. C6, not going to be soluble. Yeah, we have a polar amine, but that's not enough to compensate for the totally nonpolar aromatic ring. So it's not soluble. So we'll try its solubility in 5% NaOH. And that basically is saying, is there anything in this molecule that could react with NaOH to make a salt? And no, there is not. So we keep going and check its solubility in 5% HCl. It's either going to be soluble or it's not going to be soluble. Well, in this particular case, it turns out that it's soluble. Therefore, we stop. The rest of the solubility chart is a wash, and just as we would have predicted, this particular unknown falls into solubility class B. Something that dissolves in 5% HCl is almost assuredly an amine. So the chemistry here that explains what we just talked about is that this particular compound does not react with a base, but it does happily react with HCl to give you, aha, a salt, soluble in water because of that ionic bond. Okay, one last quick example. Again, let's predict first. If we knew the structure of our compound, we would say, ah, that's a carboxylic acid, so maybe that means it is right here. We would predict that it's going to be in solubility class S sub A, but wait. Is this going to be soluble in water? No way, no how. It's got 12 carbons, so that's all wrong. Basically, we have to see where is, okay, there's carboxylic acids that are not soluble in water, but once we treat them with a strong base and then a weak base, we make a salt. This salt, and again, this is enough to drag the rest of the nonpolar chain, 2, 4, 6, 8, 10, 12, there we go, into aqueous solution. So that's how you use the flow chart, and it's hard to get a hang of. We will go through it in lab, and that will help a little bit more, and we'll have some more examples for you if you need. Okay, now, this will be your first really hardcore notebook procedure writing exercise. Do not write your procedure up before lab. You actually write it up as you go along. Neatness sort of counts. You don't have to have complete sentences. You can make a list, but a total scribbled mess is not good. A good procedure, and this is the golden rule, what you did, what you observed, and what you thought about these observations. If you see bubbling when you add sodium bicarbonate, you should write that down, and then you should think about, what does that mean? What do you think that means? Because that's really good evidence that an acid-base reaction is taking place and that you probably have a carboxylic acid. Keep in mind, it's really crucial to get the important details in there, but some details are not important, so you're always thinking about, what do I need to write down? Looking ahead to the following week, well, and actually looking ahead, we're also still working on our ethanol. We're going to be doing some more work on our cellulosic ethanol, which is just a pain in the butt. So what you did last week, you had to beat on this darn corn stover to just bust up the lignin and give the enzymes for this coming week a chance to get at the cellulose. So the first step was that sodium hydroxide hydrolysis that just tries to chomp up the lignin and clear out the way for the cellulose. This week, we'll be trying to actually do the cleavage of cellulose into the individual glucose molecules so that fermentation can take place. So again, now this is the following week. You will not have an additional pre-lab write-up, which is nice, but you will need to read some more about GC. And this pre-lab quiz coming up for This coming week, we'll deal with, for this coming week, yes, will be solubility, a little bit about waste, and any assigned reading is always fair game. So that's it. If you have any questions, you should stop by and give me a holler. Otherwise, I will see you in lab.